Okay, and so this chapter closes out this semester, and it actually has given us quite a powerful bit of tools, right? The big takeaway here is that through these different radical reactions, we have a way of halogenating an alkane. We knew how to halogenate alkenes, alkynes, but if we were given an alkane, we wouldn't have anything to do with it because they're generally not very reactive. But we can get them to be converted into an alkyl halide using these different radical reactions. Okay, and of course, from here, once we've generated an alkyl halide, we know how to do a bunch of other things. Okay, one thing to remember about the chlorine versus the bromine is just going to be much more selective. All right, so you're going to be sort of only have that 100% selectivity towards that more highly substituted carbon versus the chlorine. And we actually have a way of quantifying exactly what this is, but the moral of the story there is that the more highly substituted carbon is going to be brominated. Bromination is much more selective. Okay, but again, like, why is this so powerful? Because once we brominate something, we got a lot of things that we can do with an alkyl halide. From our alkyl halide, we can do sort of substitution reactions. We can swap functional groups, right? Almost even more powerful is we can do elimination reactions, and then from there, do another addition, do another elimination. I mean, we can move this double bond around. We have a lot of different things that we can do with our alkenes, right? We can make alkynes. Well, not with this particular example, there's too many carbons, but yeah, I mean, we just have a ton of stuff that we can do from there. So it sort of seamlessly fits in to our synthesis tool chest here, in that now we can go from alkane to just about anything that we've been able to do before. Okay, and remember, we have we learned three different radical reactions here, all of which were just halogenation reactions, but they did things a little bit differently. One was the halogenation of an alkene in an anti-Markovnikov fashion. This was a reaction that we actually already knew in terms of reagents, substrates, and products, but we didn't have a mechanism for. Now we have a mechanism for this, okay? We also have allylic bromination, and again, when you see NBS, you think allylic, right? So I'm trying to hammer it in your head because it's very sort of easy to accidentally do an addition to a double bond when you should be substituting the allylic carbon, a hydrogen on the allylic carbon, right? So NBS is, you're looking at that allylic carbon there. We now have a way of halogenating that allylic carbon. And then just the straight up normal old halogenation of an alkane using either Br2. We can also use chlorine, but that's just another way to generate an alkyl halide, starting with an alkane. Okay. Let me just real quick. All right, so again, let's not do that actually. Let's do this. We have an alkane, an alkene, and an alkyne. Now we know how to make this jump here. Okay, we always knew that we could make, well, we didn't always know. We knew that we could make this jump here by first doing a halogenation, and then second following it up with a strong base. Remember, they love using that amide ion. And I can go from an alkyne to an alkene using something like sodium in ammonia or H2 in Lindlar. I can even go all the way to an alkane using the H2 over palladium or platinum or nickel. But again, now I have this way of going from an alkane to an alkene, which is by first reacting with chlorine and light, and then following that up, again, a strong base. In this case, we'll just pick the sodium amide again, right? But by converting it into an alkyl halide and treating that alkyl halide with a strong base, I can get an alkene. So we've sort of now closed up all these different avenues where we can convert from one to the other and back again using these techniques.